Alright, this is number 1 from the 2010 AP Physics B exam. It is primarily a mechanics problem dealing with projectile motion and momentum and energy in there. So let's get right to it. We've got a block that's compressed to a spring. The spring pushes the block. It'll travel once it leaves the spring at constant velocity until it gets to the edge of the table. Then it will fall forward 1.2 meters while traveling down 0.8 meters and hitting a target. We want all the time elapsed from the instant block A leaves the table to the instant it strikes the floor. At this point in time, we're looking at the back half of this problem. We're looking at here the time it takes to go to this spot. Now, recognize the only thing that determines the amount of time it takes to travel forward is really the time it takes to fall downward. And at that instant, we know a lot of stuff. We know that the initial y velocity is 0. It's not going up or down at all. We're looking for my x velocity. It's my unknown. We know it will fall a total distance of 0.8 meters. We know gravity is the thing pulling it down. That's going to be negative 10 meters per second squared. We're looking for the time it takes to fall that distance. Now we do know some other stuff like dx ends up being 1.2 meters. X values will not come into play here. Remember, for projectile motion, isolate your y's and your x's. They're completely separate from each other when you do your physics. You almost always will look in the y dimension to find time, and then you're going to use that time to analyze your x dimension. However, in this example, well, that's what we're going to do in this example. However, in this example, they gave us the distance. So instead of using time to find distance, we might be using the time to find speed, which we're going to find is true for B. So for A, we're going to look at our y dimensions only. We're going to use what is typically the free fall equation. The change in distance, in this example, is going to be height, is going to be your initial y velocity times time, plus 1/2 gt squared or at squared. Since my initial y velocity is 0, I'm going to get rid of that. I'm dealing with only two variables, h and g, and they're both going to be negative. So I can really put them both in as positive. It's not going to muck up my physics. So that's what I'm going to do. And I'm going to rearrange this for time. Time ends up being the square root of 2h, or 2 delta h, over g, which is going to be the square root of 2 times 0.8 divided by 10, which ends up being radical 1.6. And let me go ahead and type that in and calculate. I'm getting a time of 0.4 seconds. So it's going to take 0.4 seconds to fall down 0.8 meters, as well as it'll take to travel the 1.2 meters. I'm going to go ahead and toss that in my knowns list here so I have it for other parts. B wants us to now determine the initial speed of the block before it leaves the table. Well, that is completely in the x dimension at that point. This block is completely horizontal. So we're going to kind of do some reverse physics. We're now going to solve for Vx knowing dx and time. Remember, there's no acceleration in the x dimension. If it helps to write a sub x, like a lot of times in class I'll say, okay, this is a sub y, which is g, and then a sub x is 0. You're welcome to indicate that so you don't forget that they're not the same acceleration. However, that's not required. Average velocity in the x dimension is change in the x distance over time. We can use this because the velocity isn't changing. So we're looking at 1.2 meters divided by the 0.4 seconds, and that's going to be 3 meters per second. Okay, I'm going to leave that as is. Now we want to calculate the distance the spring was compressed. Well, because there's no energy loss during the entire transition, and I shouldn't be using this bottom diagram for this, should I be? Okay, I gotta clean up my work. Just gonna leave this stuff up here off to the side. Alright, because there's no energy loss from where the spring was compressed to where it leaves the spring to where it leaves the table, we're really going to do an analysis via energy here. We're going to say that this initial potential energy due to the stored spring is going to equal the final kinetic energy, which is what the object will have as it leaves the table. So I'm going to say, again, PES equals KE final. This is my initial, this is my final side. So 1/2 kx squared is 1/2 mv squared. We know the velocity, it's what we just calculated. We know the mass, it was given. We know k, it was given, so we can solve for x. I'm going to get rid of my fractions. I'm going to rearrange to get x by itself. X will be the square root of mv squared over k, and I could take that v out and say it's v radical m over k if I wanted to, but I don't think that's necessary right now. At this point, I'm just going to plug in as I have it. So it's going to be 4 times 3 squared, which is 9, divided by the 650. We're going to take the square root of all of that, and we're going to get 0.24 meters. And that would be the distance that the object was compressed. Now we're going to take a new block, and we're going to take it at the end of the table, and we're going to have block A collide into block B and then fall down, and the distance it travels forward will be less because its forward velocity is less. So for D, we want to calculate the distance it travels if the original X compression is the same. Basically, that means everything up until the point of impact is the same, which means VA is still going to be 3 meters per second. But now we've got a little bit of momentum going on. A and B will stick together and they'll travel forward, so their overall combined velocity will be less than that 3 meters per second. So to do D correctly, we have to figure out the velocity of the two objects that are together. So it's momentum. P before equals P after. So the momentum of the objects in the beginning must equal the momentum of my objects at the end. Well, in the beginning, we only have one object, so that's the mass of object A times the velocity of object A. At the end, they combine and stick together, so we have MA and MB coming together to make a new velocity that I'll write as V prime. I won't subscript it. I could write VAB if I wanted to. This is an inelastic equation. Ultimately, the velocity of the combined objects at the end is that original momentum divided by their new mass, which is going to be the 4 kilograms times the 3 meters per second. Divide that by the 4 plus another 4, or 8 kilograms. We end up getting a velocity of half of my original velocity. Now we can recognize that even though their forward velocity is different, the rate in which they're getting pulled down, gravity, is the same. The height in which they're falling is the same, which means the time it takes to travel is the same. So we're going to continue to use average velocity in the x is going to be equal to change in distance in the x, but now over time, of course, now we're going to solve for that change in distance. So delta dx is vx times time. The vx is the 1.5 meters per second. The time is that 0.4 seconds we calculated way early on. And we end up getting 0.6 meters for the distance it travels forward. Lastly, for E, we want to just figure out how much the mechanical energy compares in the beginning to afterwards, E2 being the energy just before they leave the table, and E1 being just after or just before A1 is released, so the energy here to the energy there. A lot of people will say they're equal because of conservation of energy, right? Well, where they're not. Mechanical energy is the sum of each potential and kinetic all the way across the board. Well, E2 at the end is going to be less than E1 in the beginning simply because inelastic collision, there's going to be energy lost in the environment. All right, that's it for the problem. Thank you.